What you should think about, and it's the purpose of this slide, is that generally all the substitution and elimination reactions compete. And so they're all occurring at the same time. Some are occurring much faster than others, and so we'll say those give you the major product. Some are going to be occurring much slower than others, and we'll say those are the minor products. Sometimes the text, this slide or other places, will say doesn't happen. And really what they mean by that is so slow that it's hard to detect those products. But those products are possible. They just have to go through a very high activation barrier, which means they're going to be very slow reactions and give very little product. So the two kinds of general reactions that we've seen are substitution, that is nucleophilic substitution, and these are at sp3 carbons. I want to emphasize that so that there's no confusion about it later. And beta eliminations. The substitutions replace the halogen with a nucleophile. The elimination replaces the halogen and a hydrogen with a pi bond. Here's a couple of examples of reactions. We have a tertiary iodide above and a tertiary iodide below. Those are the two reactions. They lose the halide, which gives the carbocation. The carbocation then can do E1 reactions. That is, we could pull a proton off of one of those methyl groups and make a pi bond. SN1 reactions are possible, and so if we have a solvent like water, water can act as the solvent, which is called a solvolysis. Water bonds with a carbocation, or we'll say it this way, water attacks the carbocation, making a protonated OH2 on the carbon, and that loses a proton to water solvent in order to make the alcohol. And so that's we have that substitution that's possible. And if the reaction is in ethanol, the ethanol OH, the oxygen, can form a bond with the carbocation in order to make the ether that's shown. And it's often difficult to predict how much of each product that we're going to get. As I've said in the previous slide, we expect a competition between elimination reactions and substitution reactions. So in the first one, we say we show an elimination, but we're going to get substitution there as well. Second one shows SN1, but we're going to get elimination there as well. Same in the third one. So it's easier to predict the product ratios for SN2 substitutions and E2 products. That's because they're so governed by steric interactions. So let's say all of these R's are hydrogens. So that means that we have a primary alkyl halide. That's going to go by SN2 reaction, and we're not going to do, or rather, that's what we expect to be favored if it's a good nucleophile. If it's not a good nucleophile but a strong base, we expect the elimination, the E2 reaction, to be preferred. We'll see examples of those later on. So here's some tables that give an overview of all of these different reactions based on the halide. So methyl halides, SN2 reactions only. There's no beta hydrogen, so there's no elimination, so just SN2 reactions. For primary alkyl halides, they can undergo SN2 reactions, which you have seen if we have a strong nucleophile. But recall, many strong nucleophiles are good bases. The hydroxide that they're showing you and the ethoxide, those are also they're strong bases and they're good nucleophiles. So we expect to have a mixture of SN2 and E2 reactions. Recall that in E2 you need a strong base. Those are strong bases and strong nucleophiles. If the base is a sterically hindered base, and that's what's meant by strong bulky bases, those are going to favor E2 because they're not going to do SN2 reactions. There's too much congestion in the transition state of a substitution reaction, so they do elimination reactions. There's not much congestion in an elimination reaction. Actually, and the general idea is that if you're taking off a proton, that's not going to be a problem sterically. If you're trying to bind a nucleophile with a carbon, an electrophilic carbon, that is subject to steric interactions. So for primary alkyl halide, we're not going to do SN1 or E1 either because we're not going to form carbocations. So for secondary alkyl halides, those are a little more complicated. We can do all of them for all of the kinds of reactions. SN1, SN2, E1, and E2, all of those are possible. And so for an SN2 reaction, you have to have a good nucleophile. And so iodide and acetate are shown as the nucleophiles, but there are the other ones that are in the table we saw in the previous presentation. For elimination reactions, if we want to do those, we're going to need a strong base, and those are often good nucleophiles. But the two that I've shown, tertiary butoxide and diisopropyl amide, those are the two that I've added. Those are very strong bases, but they're terrible nucleophiles because they're so sterically hindered. So if we choose the right base, that is a sterically hindered strong base, then we can prefer the E2 reaction without the SN2 reaction. SN1 and E1, these occur if you don't have strong bases. You don't want a strong base because it'll promote E2. If you wanted an E1 SN1 reaction, you don't want a strong base around, or a strong nucleophile, because those can go by E2 or SN2. If you don't have those around and you've got a polar protic solvent like water, methanol, or ethanol, you can promote SN1 and E1 reactions. And typically those occur at the same time. You see significant amounts of both product, and we often can't tell which of those is going to be the major product. For tertiary alkyl halides, no SN2 reactions, simply too crowded in the transition state as the nucleophile is making the bond to the electrophiles. Too high of energy transition state, and so we don't do SN2 reactions with those. We can do E2 reactions because in an E2 reaction, remember, we're taking a proton not off the sterically hindered tertiary carbon, we're taking it off of a beta, we're taking the proton off a beta carbon, which is next door to the sterically hindered center. And so it is possible, and you will often see an E2 reaction at a tertiary alkyl halide. At tertiary alkyl halides, also these reactions are very prone to SN1 and E1 because you can make the carbocation, and that's very stable because they're tertiary carbocations. And so once you make the carbocation, you can either pull off a proton, and that's the elimination, or you could have a weak nucleophile make a bond to the carbocation. Remember, that carbocation is very reactive. It's unstable, it's reactive, so it'll pull in any nucleophile that's around. It'll pull in the nucleophile to do a substitution product, but it also can lose a proton to do an elimination product. So here's some examples of reactions, and you should think about these. Perhaps we could talk about them in class. I have a couple of hints for you. First hint is, if you're going to heat a reaction, guess an elimination reaction. And normally I tell students that because in an elimination reaction, you make an alkene. And alkenes are typically lower boiling than the starting materials, whether it's an alkyl halide or an alcohol in particular. And because they're so so much lower boiling point products, typically you heat them up and you also distill away your product. You just boil it off, and so you drive the reaction towards the product that kind of way, often with heat. If you have a reaction that you analyze is going to be SN1, or you analyze it is going to be E1, expect a mixture of both SN1 and E1, and you should predict that mixture. If it's a hindered nucleophile that's also a strong base, you should assume it's an E2. If it's not hindered and it's a strong base, you should expect SN2 reactions, but you'll sometimes see E2 reactions as well. And for halocycloalkanes, there's a couple of things you should remember. First, you're going to do an inversion. Even if you don't have a stereocenter, that'll be important in a cyclic compound. For example, the one shown at left, the nucleophile is going to come in from the back side, and so the nucleophile, whatever that is going to be up, just like the methyl group is up, because of the backside approach. And also something to think about is that you want the halide in an axial position. You don't want it in an equatorial position. This is for both substitution and for elimination. The reason that you want it in the axial for substitution is it's easier for the nucleophile to come in from the backside approach if the carbon-halogen bond is axial. The reason for equatorial, for axial rather, E2 elimination is even more important. You need for an E2 elimination, you need the hydrogen that's coming off and the hydrogen and the halogen, you need them antiperiplanar. And to get those on a six-member ring, you need them both axial. So you need to have diaxial hydrogens for E2 reactions. If you're doing an E1 reaction, let's say that we had an extra methyl group on the carbon that bears the chlorine on the last problem, and so it's tertiary, then this doesn't matter axial equatorial because you pop it off to begin with, and then once you pop off the halide, you make a carbocation, and the nucleophile can react from either end.